Let's revisit energy, and specifically we're going to be revisiting energy in the context of collisions. We're going to be learning how to define something as an elastic collision or an inelastic collision. In fact, let's look at that definition right now. A collision is considered elastic when kinetic energy is conserved. Now, what does that mean specifically, conserved? That means the total kinetic energy of the system initially needs to equal the total kinetic energy of the system finally. Not of the individual objects. The individual objects are going to gain or lose energy dependent on how the collision occurs, but the system as a whole will have the same kinetic energy initially as it does finally if it is an elastic collision. That means we're specifically talking about kinetic energy being conserved. It's not enough to say that energy is conserved because energy is always conserved. We've talked about the fact that in our energy transformations, the energy's got to be in one of those buckets. But we're specifically focusing in on the kinetic energy bucket here. And if there's a change in that kinetic energy, we're no longer looking at an elastic collision. So it says, a collision is inelastic, that means not elastic, when the total kinetic energy initially is greater than the total kinetic energy finally. That kinetic energy hasn't disappeared, it must have transformed into another form of energy. Perhaps that's heat, sound, or the deformation of materials, so like in cars' crumple zones. Remember, energy is never ever lost, it just changes into other kinds of energy. Now I've put a warning here. It says you can only use momentum to calculate values with collisions. We're going to go back and look at some of the collision calculations we previously did, and that's when we said m1u1 plus m2u2 equaled m1v1 plus m2v2. What we were saying in those collisions is the total momentum at the start must always equal the total momentum at the end. That's always true. It doesn't matter what kind of collision we're going to be looking at. You can't do the same for kinetic energy calculations. Unless you know it's a perfectly elastic collision, you cannot, and I must repeat, you cannot assume that the kinetic energy at the start equals the kinetic energy at the end and then solve for values that way. You can only do that if you are told it is a perfectly elastic collision. If you're not told that, you need to assume that the kinetic energy at the start for the system could not equal the kinetic energy at the end. So, be really mindful with that. Warning number 2. Like I mentioned, you can never, ever lose momentum. If you think you found a situation where momentum is lost, turns out you're wrong. And also, you haven't probably considered where that momentum has gone. Sometimes when we consider situations with, something colliding with something attached to the earth, that happens, and we've got an example of that a little later on. Like I said, when you find yourself in a situation like that, consider whether it's been transferred to the earth, because the earth is such a massive object, we're not going to really notice any changes in velocity there. So let's look at the 3 broad types of collisions, keeping in mind that the total momentum is going to be equal initially to what it is finally in any of the cases we possibly ever look at. It's the kinetic energy that's going to change. So the first kind we've talked about, elastic, and the second time, inelastic. So in elastic collisions, that's tricky, in an elastic collision, there we go, the initial kinetic energy is equal to the final kinetic energy. You could do EK with the subscript, but I find it easier, otherwise we're going to have subscripts everywhere. So initial kinetic energy equals final kinetic energy. In an inelastic collision, the initial kinetic energy is greater than the final kinetic energy. That's because some of that initial kinetic energy is going somewhere else. Again, heat, sound, deformation of a material. The third and possibly most exciting kind is some sort of explosion. And this is an example where the initial kinetic energy is actually smaller than the final kinetic energy. That must be because we had some sort of chemical energy adding energy into the system here, allowing for there to be a greater final kinetic energy. So now we're going to go back to some previous examples. We're going to see whether they're inelastic or elastic collisions. I'm also going to point out the explosive one that we've got. Nice bit of revision here. We were doing collisions like this, where we were talking about the momentum before equals the momentum after, and that is always true. And remember the other thing we spoke about, if we had this object, for example, It started off with a larger velocity, it ended up with a smaller velocity. That loss in momentum was transferred to the other object here. Maybe I'll choose a different color. So whatever momentum mass 1 lost, that was gained by mass 2. Another important thing. So we looked at these examples, and we've previously done beautiful calculations for this, and I told you to leave some room. It's exactly for what we're doing now. We're going to determine the elasticity of the collisions we're looking at. So have a quick read of this one that we dealt with before, and hopefully we've left some exact values so we can determine things. Cool. So the way I set this out, I like to calculate the initial kinetic energy of the objects. Separately, I determine the final kinetic energy of the objects. And then third step, I look at those numbers, see if they're the same or different. Do not start with initial kinetic energy equals final kinetic energy. It's not mathematically or physically necessarily true. So, initial kinetic energy. That's going to be a half m1u1 squared. So we're doing the kinetic energy of the first mass with its initial velocity plus a half m2u2 squared. Kind of crazy with the 1 and the squared, but I'm sure you can manage. We are not writing equals a half m1 v1, etc. Not true. And please keep in mind, momentum and kinetic energy both use mass and velocity, but they're different. We've got a half mass times the velocity squared for kinetic energy. Don't forget that square. Okay, now we're just going to substitute. Okay, I get 99 joules. I like to put a very deliberate and methodical line between them. And now we're going to calculate the final kinetic energy. So we need to use the value that was provided in the question along with the value that we found in the question. Just double check the line before to see if we did any rounding here, and luckily with this one, no. Oh, and if you're asking, if you're thinking you could take the half out as a common factor and put everything in brackets, I don't mind. To be lazy with these calculations, I like to leave the previous number in my calculator and to just adjust that. Alrighty, 92.75. Let's not round it because we don't actually care what the number is, joules. We just care whether that number is the same or smaller than. This is not an explosion situation. We didn't have, an explosion. So we're expecting the kinetic energy to either be the same or smaller than. So here, the initial kinetic energy was greater than the final kinetic energy, therefore inelastic. Awesome. So please, 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 please set it as I'm doing it here. Initial kinetic energy, final kinetic energy, compare the two answers that you've got, and then very clearly make a statement of what that means. You mean it's an inelastic collision. It's not sufficient to just write this. You need to prove you know that means an inelastic collision. Okay, I'd like you to have a go at the next few examples. They should be relatively straightforward. I'm still going to do them videoed, just a bit sped up. So for the 2.3 recurring, I just put a bunch of 3's after the 2 here. Or you could do the fractional amount 7 over 3. I'll give you a hint. With this example where two objects stick together, this is known as a perfectly inelastic collision. So I know in advance that this situation is going to have the final kinetic energy being smaller than the initial kinetic energy. Let's do calculations to confirm that. Okay, I want you to confirm with this one, we have a bullet firing a gun, so that gunpowder has got to have chemical energy being converted to kinetic energy. So we should determine that the initial kinetic energy is actually going to be smaller than the final. That doesn't make it either an elastic or an inelastic collision, it makes it an explosion. But I just want you to practice doing this calculation to confirm. Alrighty, I really hope that you're able to understand the difference between elastic, inelastic, and explosive type of collisions. Let's now look at another example. Okay, we have a car has a mass of 1,000 kilos, and because I'm feeling lazy, we're going to make this 108 kilometers an hour. Because I can. So, 108 kilometers an hour, we need to divide that by 3.6 to get that in meters per second. That's 30 meters per second. Much nicer. Just want to do a nice round number here. We want to find the car's momentum before the collision. So this is P of the car specifically. So the mass of the car we're told. The velocity of the car was initially 30. So this one's nice. Now, the problem is this currently has 5 sig figs in VCE Physics. We need to change that to 2 kilogram meters per second. Now, after the collision, we're not asked about this, we might be later on, the car comes to a stop because unfortunately it's collided with this tree. So, we asked for the kinetic energy of the car before the collision. Now, I could go and do a half mv squared, and I encourage you to do that, but another thing you might like to know, and this is going to be really helpful in a future topic, kinetic energy is also equal to p squared on 2m. Why is that? P squared on 2m, that's equal to mv squared over 2m. So if we distribute that out, that's m squared v squared on 2m. We've got an m on the top and the bottom, and I could write that half out the front. So instead of everything divided by 2, I could write it as a half mv squared. This is most useful when you don't have v, but have m and p. So there might be examples in future where you're told the momentum of the car, but you're not told the velocity. That would be annoying that you need to go back and find the velocity before you could actually calculate the kinetic energy in this circumstance. It's not relevant here. I just wanted to show you this equation at least once before we use it in a future topic. So let's just use it now. Again, you could go back and use half mv squared and confirm that this works. Nearly forgot to square that. Okay, like I mentioned, the momentum of the car after the collision is 0 kilogram meters per second squared, as the velocity of the car afterwards is 0 meters per second. As it's come to a stop, it's collided with the tree. Now we want to find the impulse in the car. Impulse, you might recall, is equal to the change in momentum. And the change in momentum is going to be, for the car specifically we're talking about, final momentum minus the initial momentum. So the final momentum is 0 minus the initial momentum. Looks like we're calling this direction positive. Should have mentioned that previously. Because this momentum we've quoted as positive, and this velocity. So that direction's positive. So minus 3.0 by 10 to the 4 means that we're going to get a change in momentum of negative 3.0 by 10 to the 4 kilogram meters per second. And that makes sense. It started off with momentum of 3.4 by 10 to the 4, 3.0 by 10 to the 4 kilogram meters per second positively. It ended up at 0, so that change had to be minus 3.0 by 10 to the 4 kilogram meters per second. We do tend to quote impulse not in kilogram meters per second though, even though it's an equivalent unit. We tend to prefer to refer to that as Newton meters, not newtons per meter, Newton meters. That would be our preferred unit for impulse. So remember, impulse just means change in momentum. The other things to know about impulse, oops, that went funny, equals m delta v equals f delta t equals delta p. I like to remember that as a string of equations. We're told the car took 6 seconds to come to rest. What force did the tree exert? Oh, well, it's lucky we just mentioned that. We just figured out delta P, and we want to know the force. That's technically the average force because it is variable here. And we know the time period, so we'll use that. So with our sign convention here, it's indicating that force is to the left. Does that make sense? Well, yeah, it certainly does. That car is experiencing a force in this direction due to that tree. So that's where that negative, or that's what that negative means and where that negative comes from. So what force did the car exert on the tree? Really nice set of revision questions here. This is a Newton's third law pair. Force on car by tree. That's the Newton's third law pair, so it's the negative but same size force of F on tree by car. So that means the tree experiences a force of 5.0 by 10 to the 4 newtons to the right. So we've made it abundantly clear that it's a Newton's third law pair, and we've mentioned the direction of the force. Is momentum conserved? My answer, always. So as I said, momentum is always conserved, but we need to be a little more specific. If the car started with a momentum and then it ended up with 0, that must mean that that momentum has been transferred to the tree. So we need to do a calculation with that. You'll notice in the tree here, they've actually told us this mass because they're talking about the fact that the tree is connected to the earth, and therefore the momentum is actually not just transferred to the tree but to the tree-earth system. So although it doesn't look like the tree moves very much, particularly if it's a significantly large one and we haven't noticed it fall over or anything, that means that that change in velocity is for the tree-earth system. So what they've got is they've got an approximate amount for the mass of the earth here, and we're actually going to determine the change in velocity of the earth. You'll see it's pretty small and we won't actually observe it, but that's where the momentum is going. So I've just made a comment that the momentum of the car is entirely transferred to the tree-earth system, as the initial momentum must equal the final momentum for the entire system, and we're going to do the calculation on one of our spare pages. So we've got our data here. We are going to now set up our momentum equation. Remember, the momentum equation is always true. m1u1 plus m2u2 has got to always equal m1v1 plus m2v2. Does not matter whether it's an elastic, an inelastic, or an explosive type of collision. We're going to substitute in these values and rearrange for, I should put 2's here, sorry. We're going to rearrange for that change in velocity of the earth. Alrighty, the change in velocity of the Earth is 5.0 by 10 to the negative 21. Very, very small number. Now you might think, yeah, the Earth was rotating, so it didn't actually have a velocity of 0. We're talking from a particular reference frame. So when we get to Einsteinian physics, you will have a bit more of an understanding of what we're talking about when we say from this reference frame, the velocity was 0. So, hope this was okay for you. Please let me know if you have any questions. See you soon.